So we have seen the historical overview of what led to quantum mechanics, and also reviewed what you learned from freshman chemistry. Now let's look into the theory behind quantum mechanics. First of all, the universe has a dual nature. Each entity that exists behaves simultaneously as a particle and a wave. Each particle can be mathematically defined by a unique wave function, signified by the capital Greek letter psi. The wave function contains all information relevant to a property. For example, to determine kinetic energy, the wave function must include mass and velocity. However, it would not include things such as color, texture, or shape. Quantum mechanics says a singular entity can be described by multiple wave functions to determine multiple aspects. The wave function can be any function containing information relevant to a property. The following are the postulates of quantum mechanics. The first postulate: the physical state of a particle is described fully as possible by an appropriate wave function psi. The second postulate: the possible wave functions psi are obtained by solving the appropriate Schrodinger's equation, which will be explained later. Third postulate: every dynamic variable corresponding to a physically observable quantity can be represented by a linear operator, also to be explained later. Fourth postulate: the quantum mechanical operators corresponding to physical properties are derived from classical physics. And fifth, for the equation f caret psi equals f psi, f with a caret on top is a linear operator corresponding to a physical property, and f is the set of possible values that that property might have. So in theory, what constitutes a wave function? A proper wave function must meet the aforementioned constraints. First of all, it must satisfy the Schrodinger equation. In other words, the function f caret operating on psi must produce f psi. What this means: f caret is a linear operator defining a property. For example, kinetic energy, as you all know, is 1/2 mv squared, which is another way of saying mathematically 1/2 m times the second derivative of distance versus time, which is velocity. F without the caret represents all possible solutions. These are called eigenvalues. The meaning of this: a wave function cannot be changed by measurement. A common example: if you toss me an apple, I can't catch an orange. The wave function is said to be an eigenfunction of the operator f caret if this is true. Eigen is the German word for same. To see what this means, consider the second derivative operator. D squared psi dx squared. Posit: you have a wave function of x cubed. The second derivative of x cubed is 6x. By the Schrodinger equation, 6x is not equal to 6x cubed. Therefore, x cubed is not an eigenfunction of the second derivative. If you consider another function, cosine x, The second derivative of cosine x is minus cosine x. The same function appears. Cosine x is equal to cosine x. Therefore, cosine x is an eigenfunction of the second derivative. The eigenvalue is minus 1, since the second derivative of cosine is minus cosine. Once the Schrodinger equation is satisfied, the wave function must also be single-valued. The meaning of this is clearer. A particle simply cannot be in two places at one time. For example, x to the n can be a proper wave function. It is continuous. However, the nth root of x cannot be a proper wave function. Again, by example, look at a very simple, what is the square root of 4? The answer is either plus 2 or minus 2. Since there are two possible roots, that would mean there are two possible simultaneous states, and this is not a proper wave function. Continuing. To be a proper wave function, the third condition is that psi must be continuous. Fairly obviously, the physical meaning of this is that a particle must always be somewhere. It cannot disappear and reappear. Therefore, functions such as x to the n, sine of x, cosine of x, can be proper wave functions because they are continuous functions. If you recall high school geometry, functions like tangent and cotangent have discontinuities in them. Therefore, they cannot be proper wave functions because the particle would disappear in one place and reappear someplace else. The fourth condition, mathematically technical, is that a wave function must be what is called Hermitian. This means the integral over all space of psi star times the operator f times psi d tau must equal, positions reversed, over all space the integral psi times the operator f psi star d tau. In this notation, psi star is the complex conjugate of psi. And simpler, tau simply is a stand-in for all known variables. For example, if one's wave function was a plus ib, where I is the complex number, the square root of minus 1, the complex conjugate psi star must be a minus ib, because under this condition, psi times psi star would simply be a squared minus b plus b squared. The meaning of being Hermitian, again in the real world, is clear. The outcome mathematically must be a real number. Just as in reality, anything that happens must be real. It cannot be imaginary. The fifth condition for a proper wave function is that it must be normalized. Mathematically, this means integrated over all space and time from minus infinity to plus infinity, psi times psi star d tau has to equal 1. In this case, an integral between a and b of psi star psi is a probability function. It is the probability that the particle lies between points A and B. The physical meaning. If one sets the limits from minus infinity to plus infinity and sets the answer to 1, that means there is a 100% chance of a particle existing at some point in space at some time. This defines reality. Finally, the sixth condition. A wave function must be orthogonal. As opposed to normalization, that means over all space from minus infinity to plus infinity, the integral of psi A, psi B d tau must be equal to 0. The physical meaning of this. A wave function describes reality. If A and B are two different realities, they cannot occupy the same space at the same time. We now look on to see what constitutes an operator. An operator is a function whose solution yields a physical parameter. The operator is signified by having a caret, an upward pointing arrow, above the letter. The parameter it determines has no caret. An operator must be linear. This simply means, in this case, that they commute. The operation of A upon the result of the operation of B upon a wave function must be identical to the operation of B upon the operation of A on the same wave function. Finally, a proper wave function must satisfy the operator it was designed to operate with. This is because the operator is based on classical physics, what is known to exist. A wave function is trying to emulate existence, and it cannot be valid if it cannot yield a property that is known to exist. Common operators define common parameters. For example, linear momentum. Classically, this is denoted by the letter P and can be solved in either the x, y, or z direction as mass times velocity. As an operator, it is simply a P with a caret on top. And quantum mechanically, the operation is m times h over 2 pi I times the first derivative of the function with respect to x, y, or z. In other words, velocity. Angular momentum is another common physical property defined, again, in the x, y, or z direction as mass times the radial direction times the angular velocity in the x, y, or z direction. In quantum mechanics, this operator has a caret on top of it, again in the x, y, or z direction, and is defined as mass times the radius, identical to the classical, h over 2 pi, to normalize it over all space, times, again, velocity, the first derivative with respect to x, y, or z. Your total angular momentum is essentially unchanged. In Cartesian coordinates, angular momentum is a vector, which means the total angular momentum L is the sum of Lx plus Ly plus Lz. Similarly, as an operator, the operator L is mh over 2 pi I, Rx times the first derivative with respect to x, plus Ry times the first derivative with respect to y, plus Rz times the first derivative with respect to z. We move on from momentum to energy. Kinetic energy is denoted by the letter T. And once again, in Cartesian coordinates, it is separable. In the x, y, or z direction, the kinetic energy was 1/2 mv squared x, y, or z. Therefore, the operator would be minus mh squared over 8 pi squared I times the second derivative of the wave function with respect to x, y, or z. In Cartesian coordinates, total kinetic energy is again separable. So your total kinetic energy will be the kinetic energy in the x, y, and z direction. And your quantum mechanical operator, once again, matches classical representation and will be the result of the operation in the x, y, or z direction. Potential energy classically is system dependent. Do you have a spring? Do you have two charges? This carries through into the quantum mechanics where V caret is also system dependent. Total energy is kinetic plus potential classically. In quantum mechanics, this is given a special name. It's called the Hamiltonian operator, H with a caret, but it is still kinetic plus potential. So let's begin by looking into the meaning of the interaction between wave functions and operators in what is known as an ab initio calculation. In other words, how to create a universe with no preconceived notions. The only suppositions we have are as follows. A particle exists. A particle that exists has a mass m. In this case, it is confined to a one-dimensional universe, so it can only travel in the x direction. And that universe cannot be escaped, so it is in an infinitely deep well. This establishes what are known as boundary conditions. You have a potential energy of 0 within the well and a potential energy of infinity outside the well, so the particle cannot escape. So, under these two simple suppositions, a particle exists in a universe. What is the energy of the particle? One must first develop a wave function which satisfies the Hermitian operator, the Hamiltonian. One also decides that the potential energy V is 0 within a box of length L, the size of our universe. And therefore, since there is no potential energy, the Hamiltonian is simply minus m, the mass of the particle, h squared, over 8 pi squared I, times the second derivative with respect to the direction of motion, x squared. One examines the boundary conditions. The boundary says that to be normalized, if one integrates between 0 and L, psi squared dx has to be equal to 1. That means there's a 100% probability the particle is in the universe, or the box, and a 0% probability the particle is outside of the universe, or outside the box. One is left with a function, psi, that looks as follows. A sine alpha x plus b cosine beta x. We derive this function based on the boundary conditions. The only two mathematical functions that periodically go to zero are sine and cosine. A and b and alpha and beta will be unknown constants. Now you retest the boundary, considering there are two ends. At the first end of our universe, in this box, x is equal to 0. To test this, you simply plug in the number. Sine of 0 is 0. However, cosine of 0 is 1. Therefore, to maintain the continuity of the universe, the constant b must be 0. And our function now goes down to psi is equal to a sine alpha x. On the second boundary, what happens at the other end of the universe when x is equal to L? One recalls that sine of x equals 0 at any n pi multiples. Therefore, our wave function, to meet the two boundaries, which is to go to 0 at either x or L, becomes a sine n pi x over L. Fourth condition is to normalize this function. That means between 0 and L, the integral of a sine n pi x over L squared dx must equal 1. With some calculus that you take my word for, this is satisfied when a is equal to 1 over 2L to the 1/2 power. So our wave function is 1 over 2L to the half sine n pi x over L. We now have a proper wave function, and we can solve for the energy of this particle by solving this Hamiltonian of h caret psi is equal to E psi. The results of the ab initio calculation of the particle in a box are significant. First of all, the eigenvalues obtained from the solution to the Schrodinger equation for the Hamiltonian are E equals n squared h squared over 8ml squared. This is because sine goes to 0 at n integer multiples of pi. Therefore, significantly, the energy is a function of an integer number, n. This solution can be expanded into a three-dimensional box. Since the Cartesian coordinates are separable, the square of the wave function psi xyz d tau is simply going to be equal to the second derivative of psi of x dx, the second derivative of psi of y dy, and the second derivative of psi of z dz. The energy obtained is also separable. The total energy will simply be the energy in the x direction for the particle, plus the energy in the y direction of the particle, plus the energy in the z direction of the particle, or h squared over 8m times n sub x squared for a box of width a, n sub y squared over b squared for a box of depth b, n sub z squared over c squared for a box of height c. Again, variables are separable. Direction is discrete in Cartesian space. The total energy is a vector sum of the three components. The net result of this is that the energy of the universe is quantized. Remember, the only thing that was known was that the particle was defined to exist in space. No other suppositions were made. Therefore, the solution to the Schrodinger equation shows that anything that exists and occupies space must have quantized energy. So, for what is called the particle in the box, conclusions. First of all, math is the language of the universe. The solution to any equation describes something that can exist. If an equation cannot be solved, the thing it describes cannot exist. Secondly, and most importantly, this seemingly arcane fact has literally universal implications. It is what describes the structure of the atom, the structure of molecules, and it is what defines the interaction of light and matter.